Welcome back to part 2 of limits at infinity and horizontal asymptotes. So we'll pick up with an example. Let's compute the limit as x approaches infinity of the square root of 4x squared plus 3 minus 2x. Well, hopefully it's clear to you that as x is increasing without bound, that this is going to increase without bound, and that this is going to increase without bound. But the problem is, as this gets sufficiently large and this gets sufficiently large, we can't say that this limit is infinity minus infinity. What does that mean? That doesn't make any sense. So we're going to have to do something. We're going to have to do a math trick here, and it's actually a math trick we've done before. We're going to multiply by the conjugate. So we'll take this limit right here. Now I realize this isn't a rational function, but you can make it into a fraction by putting it over 1, and we're going to multiply the top and the bottom by the conjugate. And when we do, remember this is over 1, when you multiply your numerators together, you're going to get this term squared minus this term squared over 1 times this conjugate denominator. Now you'll notice that the square root and the square are going to cancel, and 2x squared is 2x times 2x or 4x squared. And now what do you notice? 4x squared minus 4x squared is going to give us 0, and we're left with 3 at the top. Now, as we said, as x increases without bound, this square root of 4x squared plus 3 is going to increase without bound, and this 2x is going to increase without bound. So add two very large numbers that are increasing without bound, it's just going to increase even faster without bound. And when you take 3 and you divide it by a really big number, you're going to get a really small number close to 0. So this limit actually goes off to 0. Now, because the limit as x approaches infinity of f of x gave us a finite value, 0 here, that tells us graphically that we're going to have a horizontal asymptote at the horizontal line y equals 0. So let's look at the graph of this function. And what do you notice? As x is increasing without bound, it looks like it's leveling off at that horizontal line y equals 0, which is the x-axis. Now what I want to talk about are infinite limits at infinity. So as x increases without bound, f of x increases without bound. Or as x increases without bound, f of x increases negative without bound. As x increases negative without bound, f of x increases without bound. Or the case where x increases negative without bound and f of x increases negative without bound. Now, in previous lectures, we've discussed that if the limit as x approaches infinity of f of x gives us a finite value, we would have a horizontal asymptote. But notice these are not finite values. And we also talked about if x approaches a finite value and you get plus or minus infinity as your limit, that you would have a vertical asymptote. But again, these are not finite values. So what does that mean? Infinite limits at infinity do not give us vertical or horizontal asymptotes. So let's take a look at a simplistic example. Let's look at the function f of x equals x squared. Now notice your x is being squared, so 10 squared and negative 10 squared, because a positive squared and a negative squared are both positive. 10 squared is going to be 100, negative 10 squared is going to be 100, so plugging in positive or negative values are going to give you the same answer. So let's see what happens to this as x increases without bound. Let's pick really large x values, either positive x values or negative x values. So if we plug in plus or minus 10, positive 10 squared is 100, negative 10 squared is 100. Plus or minus 100, plus or minus 1,000, and keep going. So as x increases without bound and as x increases negative without bound, you can see x squared, which is our function, is increasing without bound in the positive direction. So what does that mean? That means the limit as x increases without bound of x squared is infinity. That means as x increases without bound, x squared increases without bound. And then the limit as x approaches negative infinity, so as x approaches negative infinity means x increases negative without bound, then your function is still increasing without bound. So the limit as x approaches negative infinity of x squared is equal to infinity. So what does that mean? As x increases in the positive direction, as x increases in the negative direction, both of those are causing your function to increase without bound. Well, let's look at the function x squared. Let's look at the graph of that. As x increases without bound, remember this goes forever and forever and ever in that direction. And as x increases negative without bound, the function is going to continue to increase with no bound forever in that direction. So it makes sense, right? So let's take a look at another example. Let's find the limit as x approaches negative infinity of x squared plus x. So what's happening? X is increasing negative without bound. X is a negative value. When you take a negative squared, you always get a positive. Plus, this is negative. Well, it should be pretty clear that as x increases negative without bound, that x squared is going to increase without bound. And that as x increases negative without bound, that x is going to obviously increase negative without bound. But we can't say that the limit as x approaches negative infinity of x squared plus x is negative infinity squared plus negative infinity, because that gives us infinity minus infinity. And what does that mean? You can't do it. It doesn't make any sense. So we're going to have to do something else. So let's look at this x squared plus x. Well, what do x squared and x have in common? They both have an x. So let's factor one out. So we're taking the limit as x approaches negative infinity of x times x plus 1. Look back at your limit laws and you realize that you can take the limit of x approaches negative infinity of x times the limit as x approaches negative infinity of x plus 1. Now, as x increases negative without bound, well, x increases negative without bound. And as x increases negative without bound, then x plus 1 increases negative without bound. So when you take these two limits, this limit gives you negative infinity and this limit gives you a negative infinity. So that's representing that they're giving you very, very large numbers in the negative direction. Well, when you take a negative times a negative, we get a positive. So really, the limit as x approaches negative infinity of x squared plus x gives us positive infinity. Let's look at one more example. Let's find the limit as x approaches infinity of x cubed minus 4x over 3 minus x squared. Now, here we can do what we did in the previous video, where we can divide the entire numerator and the entire denominator by the largest power of x in the denominator, which is x squared. So when we do that and we separate that, we get x cubed over x squared and we get minus 4x over x squared. And we get 3 over x squared and x squared over x squared, which reduces to x minus 4 over 3 over x squared minus 1. So let's look at these. Let's look at that numerator and that denominator, right? So clearly as x is going off to infinity, that numerator, x minus 4 over x, is going to go off to infinity as well, right? This is going to increase without bound. This is going to go to 0. And then let's look at that denominator. 3 over x squared minus 1. This is going to go off to 0, and then this just stays as negative 1, so we have 0 minus 1 or negative 1. So now let's put that back together with our limit. The limit as x approaches infinity here, the numerator we just said is shooting off to infinity, the denominator is going to negative 1, and a positive divided by a negative, this limit goes down to negative infinity. I challenge you to take this function, graph it, and see if it graphically lines up what we just showed analytically. That's it for limits at infinity and horizontal asymptotes. I guess I graphed it for you. You're welcome. And that's it. Have a great night, and see you soon.